Hello students, in continuation with our series on case studies question, today we are going to take up questions on magnetic effect of current and magnetism. In our first discussion on case studies series, we have discussed what are case studies questions, why they have been introduced there in the syllabus and in the question paper, how we should prepare for case studies questions, and what is the proper way to answer such questions there. We have taken few sample case studies questions. After that, we have started chapter-wise case studies questions. First, we have taken electrostatics. After that, we have taken current electricity. And in that sequence, today we are taking questions on magnetic effect of current and magnetism. Let's continue our discussion on few more questions of case study on magnetic effect of current and magnetism. Next case study. Moving coil galvanometer operates on permanent magnet moving coil mechanism and was designed by the scientist D. Arsenal. Moving coil galvanometer are of two types, suspended coil and second pivoted coil type or tangent galvanometer. Its working is based on the fact that when a current carrying coil is placed in a magnetic field, it experiences a torque, and this torque tends to rotate the coil about its axis of suspension. So it is basically the basic principle of working of galvanometer there, and one diagram is also given there. Now this is the diagram which is given, and this is concave shaped just to have a radial magnetic field, and this is the pointer there, and the calibration is there. So let's see the different questions which are there. The first one is, a moving coil galvanometer is an instrument which is used to measure EMF. This is not correct. It is used to measure potential difference. This is not the correct one. It is used to measure resistance. And the fourth one is given as, is a deflection instrument which gives a deflection when a current flows through the coil. Now this is the correct one. So the fourth one is the correct. Now let's see the next question. To make the field radial in a moving coil galvanometer, options are: number of turns of the coil is kept as small, magnet is taken in the form of a horseshoe, poles are of very strong magnets, and the poles are cylindrically cut. So this is the correct one. That is the fourth one. It has basically a radial shape so that magnetic field which is there will always be perpendicular to the vector area there. Take the next question. The deflection in a moving coil galvanometer is 1. Directly proportional to the torsional constant. Second, directly proportional to the number of turns of the coil, inversely proportional to area, and inversely proportional to the current in the coil. Now, if you take a moving coil galvanometer, the torque it experiences, this is given as your NIAB sine pi by 2, because we have taken the radial magnetic field. So in that case, it is your sine pi by 2. And this is equal to C into theta. So obviously, if you consider, it is your theta will be equals to NIAB divided by C. So the deflection, if you are taking directly proportional to torsional constant, wrong. Directly proportional to number of turns of the coil, this is the correct one. Inversely proportional to area of cross section, this is wrong. Inversely to the current, that is also wrong. So the second one, that is B option, is the correct one. Now let's take the next one. In a moving coil galvanometer, having a coil of n number of turns of area capital A and carrying current I is placed in a radial magnetic field of a strength B. The torque acting on it. Now we can see this particular expression, NIAB sine pi by 2. So the torque is there, NIAB. So this is the torque acting on the coil there. So if you see the different option, the fourth one is the correct option there. Let's take next question. To increase the current sensitivity of a moving coil galvanometer, we should decrease. Now see, what is the current sensitivity? It is your theta by I. And as it is your theta by I, in that case, this is your NAB divided by C. Because we have already seen the expression that it is your NIAB, this is your C theta. So theta by I, from this expression if you take, it is your NAB by C. So what we should decrease? So for decreasing, and that is to increase the current sensitivity, it is the C term. If you are decreasing, then this term will increase. So if you decrease C, then the current sensitivity will increase. So that means the strength of magnetic field wrong, torsional constant of the spring, this is the correct one. Number of turns you need to increase, and the area of the coil also you need to increase there to increase the current sensitivity. So the correct option for this one will be the second one, that is torsional constant of spring. Let's take the next case study. Magnetic field lines of Earth resembles that of a hypothetical magnetic dipole located at the center of the Earth. The axis of the dipole is presently tilted by approximately 11.3 degree with respect to the axis of the rotation of Earth. The pole near the geographic north pole of the Earth is called as the north magnetic pole, and the pole near the geographic south is called as the south magnetic pole. This is one diagram they have given, and in this particular diagram you can see this is the tilting which they have given. What was your 11.3 degree there with respect to the axis of rotation of the Earth there. Now let's see what are the different questions which are given there. The strength of the Earth's magnetic field varies from place to place on the Earth's surface, its value being of the order of. Now this is of course not mentioned there in the passage there, but the Earth's magnetic field is of the order of 10 to the power minus 5 Tesla. So that means here if you consider 10 to the power 5 Tesla, wrong, 10 to the power minus 6 minus 5, C will be the correct option there, 10 to the power minus 5 Tesla. Next one is, a bar magnet is placed north-south with its north pole due north. The point of the zero magnetic field will be in which direction from the center of the magnet? Remember, you are keeping the magnet in the north-south direction, and its north pole is in the due north direction there. So that means it is in the direction of the magnetic field there. You want the magnetic field, the point where the zero magnetic field will be there. So it will be in which direction? Now here, if you consider that this is suppose the Earth, this is the magnet which we have taken, and this is also kept there in the same direction, north-south there. So obviously Earth's magnetic field is also in the north-south direction, and the magnetic field due to this is also in the same direction. But for the magnet, if you want the point of the zero field, magnetic field, if you consider the equatorial plane for this one, that is the magnet, its magnetic field will be in this direction, perpendicular to the equatorial plane, but in opposite direction to the magnetic dipole due to the magnet. So it will be in this direction. Due to Earth, it is again, it is north to south, that means it is in this direction. So they can cancel one another. So it is basically in which direction? It is there in the east-west direction. That is the correct one there. North-south is wrong. East-west is the correct. North-east and south-west wrong. None of these. So second one is the correct option there. The value of angle of dip is 0 at the magnetic equator because now at the magnetic equator, if you consider you have a freely suspended magnet, it will get aligned in the direction of the magnetic field. So here it will be horizontal there. Angle of dip will be 0. So because if you consider BV vertical component, it is your B sine delta, horizontal is your B cos delta. That is why tan delta is your BV by BH. So at the value of angle of dip is 0 at the magnetic equator because here at this particular case delta is 0. If delta is 0, it means this vertical component will be 0 there. So that is the correct option there. Value of h is 0. This is wrong. It has horizontal component at that point. The angle of dip at a certain place where horizontal and vertical component of Earth's magnetic fields are equal. Now again you can take this tan delta is your BV by BH. Both are equal, so they will cancel out one another. That means this is your 1. So that means delta is equals to 45 degree. So the fourth one is the correct option there. Let's take next question. At a place, angle of dip is 30 degree. If horizontal component of Earth's magnetic field is H, then the total magnetic field. Now we are just equating horizontal component, angle of dip and magnetic field. So the relation between them will be BH equals to B cos delta. So here it is given the horizontal component, you are representing it as H. B is there, angle of dip is 30 degrees. So it is your cos 30 degree. So that means B, if I consider, it is your H by cos 30 degree. Cos 30 degree is your root over 3 by 2. So it is your 2H by root 3. So third one is the correct option. Let's now take the last case study question on magnetic effect of current and magnetism. A galvanometer can be converted into voltmeter of given range by connecting a suitable resistance RS in series with the galvanometer, whose value is given as RS equals to V by Ig minus G, where V is the voltage to be measured, Is is the current for full scale deflection of the galvanometer, and G is the resistance of the galvanometer. Series resistor RS increases the range of the voltmeter and effective resistance of the galvanometer. It also protects the galvanometer from damage due to large current. Voltmeter is a high resistance instrument and it is always connected in parallel with the circuit element across which potential difference is to be measured. An ideal voltmeter has infinite resistance. In order to increase the range of the voltmeter n times, the resistance to be connected in series with the galvanometer is Rs equals to n minus 1 into G. The first one, a 10 milliampere current can pass through a galvanometer of resistance 25 ohm. What is the resistance? What resistance in series should be connected through it so that it is converted into a voltmeter of 100 volt? So you know that if you want to convert it into a voltmeter, in that case the value of the shunt resistance is V by Ig minus G. So the voltmeter range is given as your 100 divided by the maximum current that can pass through the galvanometer. This is given as your 10 milliampere. So it is your 10 into 10 to the power minus 3 minus the resistance of the galvanometer, which is your 25. So here if you consider, it is your 10, because 10 will get cancelled. So it is your 10 to the power 4 minus 25. This is your 10,000 minus 25. So this is your 9975. So that means the fourth one is the correct option there. Next question is, there are 3 voltmeters having ABC having the same range, but their resistances are 15,000, 10,000 and 1,000 respectively. The best voltmeter amongst them is the one whose resistance is. Now in this case, if you consider, the voltmeter will be giving you reading with more accuracy there if resistance is large. So obviously the voltmeter with maximum resistance will be considered to be best among the given one. So here it is your 15,001 is the correct one. So that means this is the correct option. Let's now take the next question. A milliammeter of range 0 to 25 milliampere and resistance 10 ohm is to be converted into a voltmeter with range of 0 to 25 volt. The resistance that should be connected in series. That means again we want the shunt resistance value. So this is your V by Ig minus G. Now V, voltage range, we have taken 25 as the permissible current there. So it is your 10 to the 25 into 10 to the power minus 3 minus resistance of the ammeter. That means this is your 10. So that means here, if you consider now it is your 1000 minus 10. So obviously 990 ohm there. So if you look at the different option, third one is the correct one. Let's now take the fourth question. To convert a moving coil galvanometer into an ammeter, if you want to convert a galvanometer into an ammeter, we should connect a low resistance shunt in parallel with it. For voltmeter conversion, we connect a high resistance shunt in series with it. So here, high resistance R is connected in parallel, wrong. Low resistance connected in parallel, this is correct one. Low resistance in series, high resistance in series, wrong. So that means the second one is the correct option here. Let's take the next question. The resistance of an ideal voltmeter. An ideal voltmeter should have resistance infinite, so that minimum current passes through it and maximum goes through the circuit across which you want to measure the potential difference. So obviously it should have the infinite resistance. These were our discussion of case studies questions on magnetic effect of current and magnetism. In our next discussion, we'll take up case studies questions on electromagnetic induction.